Good morning, good afternoon, or good evening, everybody, wherever you may be, and welcome to this AWS 201 webinar. My name is Markku Lepistö. I'm a technology evangelist at Amazon Web Services. And today, we will be talking about IoT, or Internet of Things, or smart devices powered by the cloud. And normally I work out of Singapore, but today I happen to be in the sunny city of Seoul, Korea. So greetings from Seoul. This webinar is a little bit different. This is an introductory webinar on the topic of IoT devices together with the AWS cloud. So we are really excited to hear your feedback on this if you want us to deep dive more and show you more angles and aspects on how to build IoT solutions on AWS. So without any further ado, let's get going. And first, let's start with really simple and short housekeeping items. So you have a questions panel in the GoToWebinar tool. So at any point during the webinar, you can use that to post questions, and we will be answering as many of those as we can. And then the reminder, please fill in the survey and tell us how you like it, and especially if you want to see more Internet of Things with AWS webinars or other types of content. So let's start the show. So today we will be talking about smart devices powered by the cloud. But first, what are these smart devices? What devices are we actually talking about? Well, nowadays, as you know, more and more devices, physical devices all around us are connecting to the internet. So you have wearables that are tracking your health and your activities. You may have fridges, you may have coffee machines or drones flying around. Many of them are connected to the internet. And many of them are now programmable because of prototyping boards or microcontrollers such as the Raspberry Pi, the Arduino, and many others like that, which are cheap. Many times they are open source hardware and they are readily available and they are easy to use to connect to the devices. But are these prototyping boards and microcontrollers smart? Well, let's take a look at two of the maybe most popular ones. So we have the Arduino Uno board, which is the most common Arduino board currently. It's not actually a computer. It's considered a microcontroller. So when you look at the hardware specifications of a typical Arduino board like the Uno, you can see that it only has a 20 megahertz CPU, which is 8 bits, not gigahertzes, megahertzes, only a couple of kilobytes of memory and storage. So it's not really a powerful computer. When you look at the Raspberry Pi, which is representing already a general-purpose computer, just a very small and cheap one, you can see that it has far more CPU, memory, etc. capabilities, but it's still not a very powerful computer. However, these boards and many others like them are really handy at connecting and controlling the devices, the physical world around us. So what you can do with these boards and the physical electrical systems around them is that you can make them see and hear. So you can connect sensors to your devices, like cameras, microphones, thermometers, accelerometers, gyroscopes, etc. So that the devices can see and hear and sense the world around you. And then you can connect actuators to your devices, things like motors, relays and switches, so that your devices can manipulate the physical world around it. And then finally, of course, you can attach wheels, propellers, or rotors so that your device, if needed, it can fly, crawl, or swim. But there are challenges. When we are talking about Internet of Things solutions, when you become popular, you will easily have thousands or even millions of these small devices that are connected to your solution and that may be producing a lot of data. And on the other side, you may easily have millions of customers or consumers of your data and users for your system. So by definition, we are talking about distributed systems at very large scale. So how does the cloud come into the picture here? Well, the cloud infrastructure, utility computing, gives us many things. And amongst other things, it gives us practically unlimited storage capacity, which is kind of like memory, and practically unlimited compute capacity, which is processing logic. So what do you get when you have a lot of memory and a lot of processing logic? In effect, you get a very large brain. So what the cloud can do is that it can complement the picture in your IoT solution and it can be the brain that is receiving the sensor data from your devices. It's making sense of those. It's storing the data, computing, analyzing on it, and then you can have a feedback loop where the cloud backend systems with the logic are then controlling with the feedback control your devices and your solutions. Then you don't have to have the heavy computational and processing capacity on the devices. That would make them larger and more expensive. You want to keep them simple. So that's one way how you can build smart devices powered by the cloud. And now I'd like to show you a few examples. The first one is the Illumina DNA sequencer. So when Illumina built this device is reading the DNA swab, so it's scanning the DNA of the sample. But rather than build a supercomputer inside each of these boxes, what the Illumina unit does is that it reads the sample, it uploads the data to the Amazon cloud for storage, for processing, and for the applications that they provide to their customers. Another example is GE, or General Electric. They build, for example, very large turbines. And they have equipped these turbines with a range of sensors. And these sensors are streaming the data, the health and the parameters of the turbines up to the AWS cloud. And GE are making artificial intelligence processing in the cloud, and then they are optimizing with the feedback loop the parameters on these turbines to get greater efficiency. And with devices this large and this expensive, getting efficiencies with this analytics is really useful and good for their business. More examples. This is the Ocean Observatories initiative. They have deployed thousands of sensors in the oceans all around the world, measuring things like the water temperature, the ocean currents, maybe the sun, ultraviolet rays, etc. And they are streaming and sending all this data back to their offices. And what these guys do is that they are then uploading the data with dedicated AWS Direct Connect links to the Amazon cloud for storage, and the scientists are no longer limited by lack of IT capabilities. They can then analyze the data and do science on the data using the computational capacity of the cloud. And it's not just here on Earth. Our good friends at NASA JPL are also observing, analyzing, and then driving the Mars Curiosity rover using the AWS cloud. So Curiosity has a lot of sensors, taking pictures, stereographic pictures with the different cameras and other sensors, sending the data back from Mars through the Deep Space Network into the JPL laboratories in Pasadena, California, where it's uploaded to the AWS cloud for storage and then processing. And for NASA, the time for results is critical. So the faster they can compute and analyze the data sent by Curiosity, the faster they can make a decision what to do next. And then they send the command back to Curiosity. And they can do more science when they have been now able to accelerate this cycle leveraging the cloud. But in effect, the Curiosity Mars rover is an Internet of Things device, not just on Earth. So coming back to Earth, another example, the Climate Corporation. They are gathering billions of soil observations and mashing those up with millions of daily weather measurements. So basically, the Climate Corporation is providing insurance for farmers. And if there's too much rain, or if there's not enough rain, then the crops will suffer. So in order to calculate then the risk analysis and calculate the insurance, they are simulating based on the weather data, based on the soil data, how the weather patterns might be changing. So in order to run these simulations, they are collecting over 5 trillion data points from all these sensors. And they are spinning up 5,000 to 6,000 node Hadoop clusters on the AWS cloud to accelerate then the analysis and simulations. Now, talking about simulations with Internet of Things, taking into account that if and when you go popular and go big, you will have potentially millions of devices and millions of customers at very large scale. So how do you get started? Basically, you want to do some capacity testing, functional testing, and other types of testing, and it's really easy to leverage the cloud services for simulations and testing. So what you can do is that you can replace your Internet of Things devices with simulators running on EC2, for example, maybe with pod instances. And on the other side, you can then simulate your customers and clients, again with EC2 instances. And to get going, easy, fast, and cheap, you can just maybe spin up one instance to do development and functional testing. When you need to do testing at very large scale, you can deploy thousands of instances. When you need to run the test, when the test is over, you shrink your system back to maybe one instance or none. And because AWS platform provides utility computing, just like water and electricity, when you switch off the resources, the metering goes down to zero. Now, I'd like to show you a live demo. And in this demo, I'd like to show you 3 different Internet of Things devices that are interacting with the AWS cloud for the processing and logic. The first device is the Arduino Yun. The Arduino Yun is the first Arduino board, first official Arduino board that has Wi-Fi. So it has Wi-Fi connectivity, which makes it a nice and interesting board to send data up to the cloud. And it so happens that the official logo of the product has the cloud in the name, in the logo, and the Chinese character Yun means cloud. So this is a microcontroller. The next device in our demo arsenal today is the Raspberry Pi. And the third device is a very new device from a company called Spark.io. It's the Spark Core. It's a very, very small and interesting and nice microcontroller that is also Wi-Fi enabled. So these are the 3 devices. And this is the architecture that I will be showing to you today. The Arduino Yun has a sensor connected to it. I'm using a 3-axis accelerometer. So basically, this is an earthquake sensor network. So the Arduino is going to be reading the accelerometer value to see if we have an earthquake happening. Now, there are many options how you can then post the data up to the cloud. In this particular example, I'm using MQTT, which is a lightweight messaging protocol. So the Arduino is reading the accelerometer value and then publishing the values, the sensor readings, to the Raspberry Pi. And because the Raspberry Pi is a full-blown computer, I've installed the Mosquito MQTT broker or server or service on the Raspberry Pi. I've also installed the AWS SDK for Python or Moto. And then my colleague has published in GitHub, you can find it in GitHub under AWS Labs, a piece of code called MQTT Kinesis Bridge. So leveraging this code, this library, the Raspberry Pi is able to then post the sensor readings to Amazon Kinesis, to our real-time streaming data service. And on the other side of Kinesis, I'm running a live dashboard. This is the earthquake sensor dashboard. I'm running it on AWS Elastic Beanstalk for the convenience of just deploying and running my application in the cloud. Now, this is how I receive the sensor readings, and I will show you the visualization next. What happens if there's an earthquake? So if my application running on Elastic Beanstalk detects that the sensor values are going over 5 Gs, something is happening. So then we need to notify the operations people. That would be my phone in this case. So when my application realizes that the sensor value received is showing an earthquake of over 5 Gs happening, I'm leveraging the Amazon SNS or simple notification service to send a mobile push message to my iPhone. So that's the first alert. Now, if the sensor readings are getting even worse, that there's a real earthquake happening, then my application is calling the Spark APIs. They run their platform on the Amazon cloud as well. And leveraging the Spark API, I'm calling the alarm function on my Spark Core. And then my Spark Core is going to be sounding a really loud alarm using a physical alarm lamp that you will be seeing soon. So this is the physical setup, if you will. Now let's switch to the demo. So let me show you first the devices in question. Just give me a second, please. We need a small video camera here. So I'm using my phone as a video camera, if you will, using AirPlay. There you go. You should be seeing that on your screens. So let me introduce the devices to you. So first of all, here I have the Arduino. So this is the Arduino Yun microcontroller. This is the first IoT device in the demo arsenal today. And you can see that there are some wires connected to the Arduino Uno. So this particular thing here is the 3-axis accelerometer. So this little chip here is reading the G-forces, if you will, when I'm moving it around. And the Arduino Uno is powering that sensor with 3.3 volts. One of the cables is black, it's the ground. And then the 3 cables here on the right side are the sensor reading values for the X, Y, and Z axis. And the Arduino is reading the sensor value. And then, on the other side of the Arduino, I have an analog display. So basically, I've connected a servo motor to the Arduino. And as I move around this sensor here, it's going to be moving my servo here. There you go. Okay, what else do I have here? I have here the Raspberry Pi. And the Raspberry Pi is a general purpose computer here. And as the Raspberry Pi is receiving the messages from the Arduino, it's leveraging the AWS SDKs and then posting the sensor ratings up to the Amazon Kinesis stream. And then to complement the picture, this is the Spark core. So the Spark core itself is that tiny little device on the breadboard there. It has a blue light demonstrating that it's connected to the internet. And then the device that I have connected to the Spark core is a relay. So it's a relay switch. And I've built a function on the Spark core, which I will be showing you later. And when I call the function, the Spark core is going to trigger 5 volts to the relay here. And the relay has a magnetic switch. And when the switch triggers, or basically opens the circuit, then we will be having an alarm with this large alarm lamp here. Okay. Now, small network issues. Give me a second here. Just a moment. Oh dear. Let me reconnect my Raspberry Pi. Anyway, then you will see from scratch how this is going. So my Raspberry Pi probably timed out on the wireless LAN. I'm connecting it back. Just a second. And then we get to the live demo. So just to let you know what's happening here, I have a local Wi-Fi network, and all my devices are connected to the same Wi-Fi. And one reason for that was the AirPlay functionality. I'm able to show you a video camera feed, if you will. So now my Raspberry Pi is back. So let's just SSH into the Raspberry Pi. And let me show you what I'm running here. So basically, let's check if we are running the Mosquito server. Yes, we are. So in the init scripts of the Raspberry Pi, I'm running Raspbian there, which is a Debian distribution. I'm running the Mosquito server. So Mosquito is the server side of the MQTT protocol. So now the Raspberry Pi is on the local network and it's able to receive MQTT messages. And then I downloaded from GitHub my AWS colleagues MQTT Kinesis bridge code. So this small Python code is then receiving the MQTT messages and then connecting with my Kinesis stream on AWS and then uploading or posting the sensor readings that the Arduino sends to the Raspberry Pi to Kinesis. And now you can see on your screen that we are basically posting messages to Kinesis. Let me show you with the video camera again. So you can see the sensor values there. Those are the values that are going to Kinesis. And let's have a video camera. There we go. So now, as I turn the accelerometer around, you can see that the analog readout or gates there, which is actually a servo motor connected to the Arduino, is getting a bit hectic. So as I turn the accelerometer one way and then the other way, you can see that the sensor reading is manipulating the servo motor, and the servo motor is basically an analog readout of gates. And you can see on the screen as well, if you look at the SSH to the Raspberry Pi, that the sensor values are changing. Let's come back to that later. Next, let me show you what we have on AWS side. So first of all, I have a Kinesis stream. So I've created a Kinesis stream. I happen to use the Tokyo region in this case. I'm in Korea, which is quite near. So I have created a Kinesis stream called Sensor Grid. So the Raspberry Pi is receiving the sensor readings and posting them using Boto, MQTT, Kinesis bridge to this Kinesis stream. So you can see here that we get values. So this particular Kinesis stream is active and it's receiving data from the Raspberry Pi. And then in Elastic Beanstalk, I'm running my application. The Elastic Beanstalk application looks like this. It's a PHP application that's receiving the data from the Kinesis stream. So it's consuming the data coming from Kinesis. And then basically it's just live graphing those. So let's manipulate the sensor a little bit again so you can see the effect. So let's add some G's here. Let's have some positive G's first. There you go. After a while the graph is going to react. There you go. Let's have some negative G's, maybe -3, -4. Soon it's going to drop down. There you go. All right. So this is an end-to-end solution now. But what about the alarms? Let me show you the alarms. So let's pull my phone back here. So this is a live feed from my phone. And now let's try to have an alarm. Let's first try to have a notification alarm to my phone. So when the value exceeds 5 Gs, then we should get a push notification alarm to my phone. So let's try to have -5 Gs or so. There you go. So now we are getting about -5, -5.18, and there you go. So now you can see that we start getting the alerts that, hey, something is happening. There's maybe an earthquake coming. Be careful, all right? What happens if we exceed 6 Gs? Then this guy will wake up. So if the sensor value exceeds 6 Gs, then we are sending an API call to that device, which is the Spark core. It's going to flip the switch on the relay, and then we are going to have a big alarm. Let's try that. I'm trying to now get +7 Gs. Oh dear, there you go. So that was the physical alarm when we exceeded 6 Gs of acceleration. So that was the earthquake alarm. And it worked. Now, let me show you a little bit more. Just going to show you how I built this, in case you're interested. So here on the screen now, you can see the Arduino SDK. So this is the piece of code that I have on my Arduino Yun, which is then reading the sensor value from the accelerometer and posting it to the Raspberry Pi. Basically, I'm leveraging the Yun client here, which gives me Wi-Fi or internet connection using the Wi-Fi client on the Yun. PubSub client library gives me the MQTT protocol. And then finally, the server library allows me to manipulate the server, which is moving the needle on my display. And the code is really quite simple. I'm going to show you the major parts here. My MQTT server, the Raspberry Pi, is this. I happen to use static IPs. A better way would be to have dynamic addressing and dynamic service discovery, which would be more complex but more future-proof. So in this case, I have hard-coded the address for the Raspberry Pi for the Arduino. And then quite simply what happens here is that I'm attaching the servo, so the setup is something that the Arduino executes once. The Arduino is a microcontroller. It doesn't have an operating system as you're used to. It's basically just executing that one application that you upload to its firmware. And typically you code it in C. And what happens is that first the Arduino runs once this setup function. So here I say that I have attached the servo to the port number 9 in the Arduino. We start the bridge, which gives us connectivity. And basically first I zero the server. So I set the servo to 0, my analog display will start from 0. And then the loop function in Arduino is looping around endlessly. This is your main program. First, we connect to the MQTT server using the Yun client and Wi-Fi. The Arduino is connecting to the Raspberry Pi, and Raspberry Pi is running the Mosquito server. If that's successful, we are publishing Yun connected. One message to the MQTT pops up interface, and then the next piece of code is reading the sensor value from the analog port 0. So I'm reading one of the ports, which happens to be the x-axis of the accelerometer. Then there's some simple mathematics to get the g value out of that. And what I'm doing next is then moving the servo to an equivalent value. So if I read value -5, then I'm moving the servo to an angle which is roughly matching -5 on my analog gates. We wait for the servo to reach the position, we give it some time, and then finally, every second, so after 1 second has passed, the Arduino is going to be publishing the latest sensor reading with MQTT to the Raspberry Pi. And the Raspberry Pi MQTT Kinesis bridge you can see executing here. Now, how did I get the alarms? The notification to my phone was quite simple. I used the Amazon SNS Simple Notification Service. You can see here that I have one application registered in the Tokyo region, the Amazon Mobile Push Demo, and there's one endpoint, which is my iPhone. So this is the console of Amazon SNS, but how do I actually call it? Well, let me show you what I'm running in Elastic Beanstalk. So Elastic Beanstalk has the application that's consuming the data from the Kinesis stream, and then it's displaying it as a live graph. And this is the code for that piece of PHP code. So I'm going to show you really briefly how did I build the server-side application that's graphing the sensor readings and also sending the notifications. So you can see that it's PHP. This is what my Elastic Beanstalk is running. Here we initialize the Kinesis client using the AWS SDK for PHP. And we also initialize the SNS client for push notifications. Next, we are reading the latest packets from the Kinesis stream, latest records. And then what we do with the records is here. This is the most important if-then statement. Once we read the latest records from the Kinesis stream, if the value is over 5 Gs or below -5 Gs, we send a push notification to my phone. And if the value of the record that we receive from the Kinesis stream exceeds 6 Gs, then I'm calling the API of the Spark device itself. And Spark.io are running their platform on AWS, and then I'm calling my device-specific API, and then triggering the alarm. Now, how does that happen? The final piece here is the Spark itself. Interestingly, the Spark core device can be programmed using their web interface. So you can see it right here. This is the application that I've loaded on my Spark core. You can see that it looks similar to the Arduino, so it's an Arduino-like or Arduino-compatible device. And this is the code running on my Spark core. So first of all, I'm saying to the Spark core that my relay switch is connected to pin number D0, so digital pin 0. This pin I use on the Spark device to trigger the relay to either let the electricity through to the alarm lamp or close the circuit, and then the alarm lamp doesn't make a racket. What we have here then is that we define a function. So I've defined one function. This is a really simple program. It's a Spark function that I have given the name alarm. And I start by the alarm being off. And the loop has nothing. And if I call the alarm function through the APIs, then we execute this function. And it's a really simple function. Basically, we are just writing the high value. So we are raising the voltage on the relay pin. The relay has a magnetic switch. When you raise the voltage, It clicks the switch and connects the circuit, and that starts the racket with the lamp. We wait for 3 seconds so it doesn't go on forever, and then we switch off the alarm. And what I could do last is I will show you how I call the Spark devices using their command line tool. So the command is Spark that you need to install once you have the Spark devices. And let me show you the camera as well. Let's have one more alarm, but this time let's call the API from my command line. So here's my phone again. Let's have the video camera, if you will. So there's the lamp, there's the server that I was talking, there's the relay that I was talking about, the blue little box there, and that's the Spark core. And on my screen, you can see the command line. And first, we can list what devices I have. So I've given my device, or that Spark device name, Tulppa, which is Finnish for plug, kind of like a spark plug. And if I ask what functions are available, you can see that this, my device, has the function alarm available. So simply, all I need to do is using the command line tool equivalent, which will then generate the API call my device, and specifically call the alarm function. So I send the API call now, and pay attention to what happens to the alarm. Oh dear me, there we have an alarm. Good. So I really hope that you enjoyed this end-to-end demo. So we had here an Arduino, we had a Raspberry Pi, which acted as the bridge to the AWS services. Then we used Kinesis, we used Elastic Beanstalk for the live dashboard. We used Amazon SNS to send a push notification to my phone. And then finally I called the Spark API to cause a racket with the Spark device that has the alarm lamp connected to it. To summarize, to start building Internet of Things solutions on AWS, we have a range of useful services. The first of them are the AWS mobile services, and some of our latest services there that are useful are services like Cognito, and of course the SNS Mobile Push. We have the connectors to other useful services like Kinesis, pumping data into the stream, manipulating DynamoDB or S3 directly, SQS, simple queue service, or maybe the simple email service. And once you are then consuming and ingesting data from a large number of Internet of Things devices, then we have a range of big data services that make your life easier with those. So we have services that make it easy to collect and store, analyze, and then act on the data, or big data coming from your IoT solutions. That's one way how you can build smart devices powered by the cloud. And we would really be interested in hearing your feedback. So first of all, thank you from myself. I'm Markku Lepistö, an evangelist at AWS working out of Singapore, today in Seoul, Korea. And please remember to fill in the survey. We love your feedback. Your feedback lets us iterate and improve on our services. And specifically today, I'm interested in hearing how you like the introductory IoT session here. If you would like to see and hear more about building IoT solutions on AWS and how the AWS services may make your life easier with IoT. So please fill in the survey. And again, thank you very much for joining. I really hope that you enjoyed it and hope to see you next time. Thank you and bye-bye.